Oh, welcome. Thank you once again for coming. This is the fifth session of a online course, a 9-session online course entitled Introduction to Data Mining 1. And this is the PM class. And after reviewing material, the schedule in the future and the schedule for the next session, the next course that starts up after a couple more sessions, I'm going to try to stick to the original schedule. I think that's probably the best strategy when there's any doubt about what to do. So the original schedule for the fifth day was to look at regression, and so we'll look at regression in GLMs. I hope to come back to random forests, and I believe I will, perhaps in the next week or two, or at worst in the next course. But let's try and stay on topic for the time being. So we did have an exercise. Here's the exercise. I really liked this exercise. I felt it tied everything together pretty well, in the sense that it made use of both trees and forests, and in a comparative way. So let's take a look at this. What we were to do in this exercise really was to build models, build a model using a decision tree, a classification tree, and then to also build a model to predict classification of this forensic glass type using bagging, which is a technique that we really did not talk about extensively, and then random forests, and then to compare them all. So that's what's done in this exercise. It ties together that material and also brings out a couple of new points. So let's take a look at this. The data set, the operative data set, is this forensic glass data in the mass package. And what we're trying to do is predict the type of glass fragments with these various numeric predictors. So if we load up the mass library and then call the data set directly with the data statements, you'll see it down here, and now we can pop it open because it is a data frame, and we're predicting type of glass fragment. And you really don't have to understand the domain. We have WinF, we have WinNF. These are levels of glass type. We have VEH, we have CON, we have TABL, and we have head. We have at least 6 different levels for this glass type. So it is a classification task. All of the predictors that you see back here are all numeric. And so we're going to set the seed. We're going to do a partitioning of the data into both a training set and a test set. So we set the seed just so that the next time we split the data in the same way, we'll end up with the same partitions. So we do that, and note we're using the same syntax that we used last time, where we are using the sample function with replacements, and we're sampling from a sequence of 1 or 2, such that 90% of them will be 1s and 10% of them will be 2s. And so if we look, we're sampling as many times as there are rows in the data set. So when we do that, we find that we've assigned a vector here to IND, and there are 90% of the data set of the initial rows in the data set are coded as 1, and 10% are coded as 2. So we can use that just by indexing the original data set as 1 or 2. We can use that to separate out the training set into the test set. So we do that. You notice they show up down here in the workspace, whenever you partition or subset a data frame, the result is a data frame. You always get a data frame. Whenever you use column bind or row bind, you get a data frame. Data frames are very persistent, and when you start doing selections and filterings on them, the product that is output, the data structure that is output, is also a data frame. So that's what we do. Okay, so we're going to build a tree. The tree itself really is not that useful as a decision tool, but it forms the basis of many other decision tools, most notably random forests, which are an ensemble approach, as we mentioned a couple of times. And we're going to use the recursive partitioning package, or RPart. So let's do that. So we called the RPart library. Of course, you must have this installed for it to work. And then here is our model. We invoke the model, build the model using the RPart function, and we are modeling type as a function of every other variable in the data set on the training data. And we really didn't belabor this a lot before, but let's take a minute to look at this. If we do this, and if we just highlight P1, the output object, the fitted object, the modeled object, we get these rules. The rules come out like this. Really not that much there to it, evidently. But note it is a bushy tree. It builds the tree until you have all of the leaf nodes, and there really are no more breaks or divisions that you can make. But note this: if we say what's the structure of P1, which is kind of a universal, P1 is a list. It is an RPart object, but it is also a list, and it has all of this information in there. Lots and lots of information, much of which we don't even use, about weights and Y values and complexity and so forth and so on. You can access these things with some simple programs, but we choose not to do that. So the author has written it such that when we say, what does P1 look like, all we see are the rules that pop out, but there's much more behind it. And if we say, what's the class of P1, it's going to tell us that it's an RPart object, but that doesn't mean it's not a list. And we can confirm that by saying is list, and we get a true. So lists are very powerful and complex data structures, and you can use them to hold lots and lots of different information. So anyway, we're going to plot this. We say plot, and note with the RPart, the plotting is kind of clunky. When you call plot, all you get initially are just the branches, the divisions, and without any text or nodes. And to place text on it, nodes on it, you have to explicitly call out the text function. And so we see the divisions all the way down to the 6 different levels of the classification variable. Okay, so this is the bushiest tree that we can have. And normally with RPart, what you do with recursive partitioning in general, what you do is you grow a very bushy tree, and then you prune it back to the point at which the error is minimized. But we're just demonstrating the fact that we're building a tree, which is a root structure, a basic structure.